Greetings once again. This is the Pencrest High School AP Physics 1 video series. This is video 8D, Standing Waves and the Harmonic series. Now, some of the behaviors that we talked about in the last video can combine to form what are called standing waves. A standing wave is a combination of fixed end reflection and both kinds of interference. Constructive and destructive, in a stretched, flexible medium like a spring. When a standing wave pattern is created, the medium appears to vibrate in place. It's an optical illusion created by what's called an interference pattern. So this is sort of what standing waves look like. We have what are called nodes or nodal points. And these are places where the medium doesn't move very much. In between, we have what are called antinodes. The antinodes are locations of maximum displacement. So this is kind of hard to show in a static diagram. The demonstration is much better than a static image. I'll also show you a simulation at the end of the presentation here, so that you can see it. Now, in this image, waves are moving both left to right. You can see them sort of shown here. Waves are moving left to right, and the green arrow shows the waves that are moving right to left. So as they move through each other, they interfere. And in these regions, we get areas of constructive interference. We get large amplitudes. And then at the nodal points, we get destructive interference, and this is where the amplitude is effectively zero. Okay, so there's no displacement there. The wave frequencies that produce standing waves depend on several factors. First of all, the wave speed in the medium, which depends on the mass of the medium, the length of the medium, and the tension. So the wave velocity is the square root of ft times L over m, and this contributes to the pattern. A series of frequencies that will produce standing waves have wavelengths that correspond to a very particular mathematical relationship. This series of frequencies starts with what's called the first harmonic, or the fundamental frequency. This is the frequency that will produce effectively one big loop that looks like it's just going back and forth. Again, in fact, it's constructive and destructive interference. But this fundamental frequency is called f sub 1. The wavelength of the fundamental frequency, lambda sub 1, is 2 times L. You can see here that this wave pulse effectively is a half a wavelength. So the length of the medium is 1/2 of the wavelength of the fundamental frequency. As we go up the series, when we go to the second harmonic, which is also called the first overtone, we call that f sub 2, and this is the integer multiple 2 times the fundamental frequency. We can see that a full wave makes up the length of the medium. So the wavelength of the second harmonic is just L, whatever the length of the medium is. As we go up, we see that F3, the third harmonic, also called the second overtone, F sub 3, is 3 times F sub 1, 3 times the fundamental, and the wavelength is 2/3 of the length of the medium. So we see there's a pattern. The frequency of the nth harmonic, if we're looking at the fourth or fifth or sixth, n is the nth harmonic. If we're looking at the frequency of the nth harmonic, it's basically n times the fundamental. So the fourth harmonic is 4 times f1, the fifth harmonic is 5 times f1, and so on. The wavelength of the nth harmonic is 2L over n. So n is, again, whichever harmonic we're looking at, and the wavelength of that frequency is 2L divided by n. So now we're not quite at the that is all stage. So what we want to look at is a standing wave simulation. And what you're going to see here is a series of waves that are very slowly moving left to right in the diagram. These are incident waves. They're in red, as you can see. And they're moving left to right towards this barrier here, this fixed end. And when they hit the fixed end, they're going to reflect. And as they reflect, the reflected waves will appear in blue. You'll see that they will flip over as per fixed end reflection. So here's the first reflection. Here's the crest reflecting as a trough. And as the blue waves, which are reflected, as they move right to left, they're passing through the same medium. And they are interfering with the incoming red waves. And what you see in black here is what the medium actually does. So again, it looks like it's sort of vibrating in place, but we can see the spots labeled A are the antinodes. This is where the interference is constructive. We get very large wave crests and very large troughs. And then in between, tougher to see, but there's an N. These are the nodal points where the interference is destructive and the waves are constantly canceling each other out, so there's no displacement there. So what you see in the black is a standing wave pattern, and we would call this 1, 2, 3, 4, 5, 6. This would be n equals 6. This would be the sixth harmonic, assuming this was the other end of the medium. Okay, so again, that's a much better visual than any static image can produce. This is the standing wave pattern, and now we can go to that is all. So that's standing waves and the harmonic series. Until next time, enjoy. I'll see you again soon.